session. So it's a pleasure to have André now talking on the elliptic KZB Associator and OpenString integrals at Genus 1. Please go ahead.
So thank you very much, and thank you very much for the invitation. Thank you very much for joining my presentation. And as mentioned, I'm going to say something about the elliptic KZB Associator and OpenString integrals at Genus 1. Before I give the actual outline of my talk, I would briefly say or motivate what I'm going to talk about. So I think why studying string amplitude, this question has already been answered in the previous talk and also yesterday in the talks. I mean, it's a really fascinating field which combines beautiful mathematics from number theory, from algebraic geometry and so on with quantum field theory, amplitudes. You can study aspects of string theory like dualities from the point of view of amplitudes and so on. So I don't think I have to spend too much time on this point right now. So what I'm going to talk about are the endpoint open string amplitudes, and as you saw in the previous talk, they are usually described as a double expansion in terms of alpha prime, the inverse string tension, and the genus G of the underlying worldsheet. And actually, I'm also just focusing on these string contributions to the full amplitude. So that's what I'm going to refer to as string integrals. And as in the previous talk, I'm also just actually going to consider the integrands and not the integral in the genus 1 case or the modular parameter tau. So in the genus 0 case, it is known that these string integrals are linear combination of set integrals which have been introduced yesterday at Federico Zerbini's talk. The differential forms in these set integrals just form a basis of the twisted de Rham cohomology of the punctured Riemann sphere. And it is also known how to calculate these string corrections at genus 0. So there are different methods. Some examples are a method using the Behrens-Giehler recursion. Another example is a method which uses the Drinfeld associator. So, and it is exactly this method which I'm going to generalize to the genus 1 case actually. So using the Drinfeld associator, one can calculate the endpoint tree-level string integral from the n-1 point string integral only using matrix multiplication. So in the genus 1 case, Oliver Schlotter showed us last year at this conference that it is really nice to describe the string integrals in terms of so-called set tau integrals. These are actually generating series of these string integrals where some auxiliary variables are introduced, and if one then expands the set tau integrals in these variables, the actual string integrals are the coefficients we obtain from this in this expansion. And he introduced for the endpoint case a basis of n-1 factorial set tau integrals. And he also showed how to compute them using Picard iteration. Now what I'm going to do today is actually to give a slightly different point of view on how to compute these set tau integral, which uses the elliptic KZB associator. The elliptic KZB associator, as I'm going to show, is actually a generating series of elliptic multiple zeta values. And this will give us a relation which can be used to calculate the endpoint set tau integral from the n+2 point set integral. So from the, we go from the genus 0 integral to the genus 1 integral by actually geometrically, it can be thought of as a gluing together of two external states, but I will comment on that in the talk. So now let me give the actual outline. So first of all, I'm going to introduce elliptic multiple polylogarithms. I think I can be quite brief with this one. Then I will give the definition of elliptic multiple zeta value, and finally the construction of the elliptic KZB associator, and show how it is connected to a differential equation, which is called elliptic KZB equation, and actually how it relates to boundary values of this differential equation to each other. Then in the last part, I'm going to consider open string integrals at genus 1, and actually first recall the definition of the set tau integrals, show how they may be modified with an auxiliary point, and then give you some properties of this new class, of this bigger class of set 0 tau integrals, and show how they actually furnish this recursion of the string integrals. I will finish with a 2-point example. So let me begin with the EMPLs. As usually, we consider elliptic curves as a torus with model parameter tau. So the torus is described, as we already saw, as the complex plane modulo the lattice spanned by 1 and tau, where tau has an imaginary part bigger than 0. Then the elliptic multiple polylogarithms are defined as the following class of iterated integrals. So first of all, the empty integral is just 1, and then we iteratively integrate from 0 to some set, or these integration kernels gk, which we already met several times in this conference. They are given by the Eisenstein-Kronecker series. So if the series is expanded with respect to eta, one obtains as coefficients functions of z and tau, and they give us these integration kernels. Some examples include the following. First of all, we have G0, that's just 1. G1 is the Weierstrass zeta function with some linear correction. The Weierstrass zeta function is the Unicode primitive of the negative Weierstrass B function. And this G1 kernel has simple poles at each lattice points, and in particular at all the integers. And why I'm highlighting here the integers, that's because of the following reason. So if you then consider the higher integration kernels like G2 up to Gk, we find that they are polynomial of kth degree in G1. And the remaining terms in these polynomials are exactly such that they cancel the poles at the integers. So G1 is in particular the only integration kernel which has a simple pole at 0 and 1. That means that we have to exclude it here in this definition above here of the EMPLs as the innermost integration kernel. Otherwise, you would get a logarithmic divergence from the lower integration boundary from the 0 here. So in order to also include these labels in the EMPLs, you have to regularize the EMPLs accordingly. And we do that by simply subtracting this logarithmic divergence here coming from the lower integration boundary. Similarly, if you have multiple such labels, 1, 0, we just can define the corresponding EMPL and using here the right-hand side of this second equation, which is reminiscent of what we expect to find from the shuffle algebra of iterated integrals. And similarly, if we have a general such a label KRZR equals 1, 0, there's also a regularization prescription such that the shuffle algebra is preserved, and we can actually, and we have actually the full class of EMPLs with any such labels which satisfies a shuffle algebra. Again, 2 examples are the following. Maybe the most important one, at least for our purposes here, is the common tilde of 1, 0, which has this key expansion you can see here. Then a second example is this second EMPL here. As I said, the left-hand side is actually ill-defined because of this condition in the second bullet point, but we can define it just by the right-hand side, which you expect to find from the shuffle algebra. Here, everything is well-defined since we have defined the gamma tilde of 1, 0 already. Actually, I'm not going to consider the full class of EMPLs, as you can already see in these examples. I'm only considering such EMPLs which have all these lower labels 0, so we don't include any shifts in the integration kernels. And we denote this subclass of EMPLs using the notation Federico Zerbini used yesterday in his talk. So we denote them with words from an alphabet with letters x0, x1, and so on. So in general, these are free Lie algebra generators. I wrote them in bold letters because for our purpose, they are actually going to be square matrices. And in this talk, everywhere where you see some bold symbol, it is actually a matrix, or it can be thought of as a matrix or a vector. So that means that we have now this class of EMPLs. Now we can define the EMZVs. The EMZVs are just the values of these EMPLs at 1. However, again, we have to take care of the simple pole of G1 now at the upper integration boundary at 1. And if we had such a G1 integration kernel in the outermost integration, and then we would get again a logarithmic divergence. This can be again accounted for by a certain regularization prescription, which preserves the shuffle algebra. And this leads to the full class of the properly regularized EMZVs. And certain examples are that W of 1 is just 0, that comes exactly from this regularization, otherwise it would diverge. The W of 2m gives us the even zeta values. The more generic example is W of 01, which has this nice Q expansion here. So now, having defined the EMPLs and EMZVs, we can actually come to the construction of the elliptic KZB associator. In order to do so, we consider the generating series of EMPLs. That's this formal sum over all these EMPLs weighted by the corresponding word. So again, if you think of these letters X, K as square matrices, it's just a sum over matrices weighted by the corresponding EMPL. And here we restrict ourselves to the unit interval such that it's always clear which limits I'm going to take in the rest of my talk. And where I usually consider limits to 0 and 1, they always sit on this interval. So now let me state two important properties of this generating series. The first one is that it solves the so-called elliptic KZB equation. That is this differential equation here, where we find these integration kernels from the Eisenstein-Kronecker series. And actually the generating series of EMPLs satisfies this equation quite by definition of the EMPLs as iterated integrals. Then the second important property we're going to use is its asymptotic behavior close to Z equals 0. And since that's going to be quite crucial, let me go briefly through this calculation, or outline it at least. So if you let Z go to 0, all the EMPLs in this generating series, which are honest iterated integral with integration kernels that are non-singular, or at least are linear combination of such integrals, where each term has a factor which is such an honest iterated integral, all of these EMPLs vanish if you let Z go to 0, because they all then have factor of an empty integral actually. So the only ones that remain are the ones that are not such honest or real iterated integral over non-singular kernels. And these are exactly the ones which are associated with the words x1 to the power of n, which themselves are just defined as the nth power of gamma tilde of x1 divided by n factorial. That means the asymptotic behavior of the generating series of EMPLs is given by this exponential of x1 gamma tilde x1. But actually we can even go further, since we know the since we actually know the definition of gamma tilde x1. So if we recall its definition, we see here that we actually subtracted this logarithmic divergence, which otherwise would come from the lower integration boundary. But that means if you now let Z go to 0, we actually encounter exactly that divergence now from the upper integration boundary. So that means we're left with a logarithm of minus 2 pi I Z. Plugging this into the above exponential, we find the asymptotic behavior of the generating series of EMPLs goes like minus 2 pi I Z to the power of x1. So now, having these two properties at hand, we can continue as follows. So we can define the elliptic KZB associator. It is given by this product of the inverse of gamma tilde 1 minus Z times gamma tilde of Z. So gamma tilde 1 minus Z is actually also a solution of the elliptic KZB equation. That means that we have a product of an inverse of a solution times another solution of this equation, and such products are in general independent of Z. That means we can choose to evaluate this product close in the limit Z goes to 1. And in this limit, we exactly know the asymptotic behavior of gamma tilde 1 minus Z from the slide, from the previous slide. It's given by this exponential. So we just find the generating series of EMPLs and with some exponential prefactor. And if we evaluate this generating series at 1, we almost get the generating series of EMZVs, except for the fact that we had to regularize them additionally due to this divergence now from the upper integration boundary. But here in this case, this is exactly taken care of by this exponential prefactor. That means in the end, we're indeed left with the generating series of EMZVs. And we find that the elliptic KZB associator is just given by this series of regularized EMZVs. Okay, now let me come to the elliptic KZB equation. So how is this construction useful in a possible string recursion? And in order to answer this question, we consider an arbitrary solution of the elliptic KZB equation and define these two boundary values. We have to regularize, we have to use a certain regularization to define these boundary values due to the fact that G1 diverges. So this right-hand side of the differential equation has singular terms as z goes to 1 or 0. That means in order to extract some finite non-vanishing information from these boundary values, we actually have to include these two factors here. And now, how is this connected to the elliptic KZB associator? As you might expect, from the name associator, this associator actually associates or connects these two boundary values. So C1 is given by the associator times C0. And since this is going to be the backbone of our string recursion, I would like to briefly go through the calculation or to the sketch how one can show this equation. It goes as follows. So first of all, we just write down the definitions of the right-hand side. And then we remember that the asymptotic behavior of gamma tilde of z close to z equals 0 is just given by exactly this factor, but just the inverse. That means these two cancel in this limit, and we're left with these two factors here. But now again, we have an inverse of a solution of the elliptic KZB equation times another solution that's independent of z. So we can choose to evaluate it close to 1. So we can evaluate it in the limit z goes to 1. In this limit, on the other hand, we also know the asymptotic behavior of gamma tilde 1 minus z. It is exactly given by the prefactor we use to define C1. And that's how this associator equation comes about. So now, I'm actually finished with the introduction of all these mathematical concepts. Now let me go back to the string integrals, or actually these corrections in the full string amplitude. And in order to do so, I just recall the definition Oliver Schlotter showed us last year at the Elliptics 19 of these Z tau integrals, which are generating series of the actual genus 1 string integrals here. So these Z tau integrals for a given number of external states n, and there are actually n-1 factorial of such integrals, and they are labeled by permutations of the labels 2 up to n. And that's what is given by the sigma. And actually, I'm going to identify permutation with its image on these integers 2 up to n. So now let us start with the integration domain. The integration domain is actually just an integration along the full A cycle of the torus, where we iteratively integrate or the n-1 punctures Z2 up to Zn. These are the punctures from the vertex operators, and we can use the symmetry of the torus to fix Z1 to be equal 0. And then we have in the integrand two factors. Essentially, the one is the Koba-Nielsen factor. That's just the plane wave contribution from the vertex operators. And in its arguments, it has the Mandelstam variable where we find the parameter alpha prime. Maybe I should say at this point that actually we in order to have well-defined integrals, so non-divergent integral, we just restrict ourselves here to the case where these Sij's have negative real part. But I mean, that's actually the divergence behavior is quite similar to the genus 0 set integrals, because they have exactly the same kind of divergences as two punctures merge together. And actually we also don't impose momentum conservation, because in this case then we get non-trivial 2 and 3 point examples. So, and that's a bit easier to show on the slides. And on the other hand, in these arguments we have the open string Green's function. The open string Green's function can be described in terms of exactly this EMPL gamma tilde of 1, 0, and conventionally one also introduces this additional term of W of 0, 1. So now let me come to the last part of this integrand, which is this phi tau 1 of sigma. And that's actually just a product of Eisenstein-Kronecker series. I'm going to call it, or we're calling it, the chain of Eisenstein-Kronecker series for the following reason. So if you consider the identity sigma, so the phi of 1 to up to n, this is a product of n minus 1 Eisenstein-Kronecker series. So this n minus 1 n is just the Eisenstein-Kronecker series evaluated at the difference here of these labels, and this eta n is just the auxiliary variable we find here, and when we expand the Eisenstein-Kronecker series to get our integration kernels. And now let me say a few words more about the structure of these products. So if we begin here at the rightmost factor, fn minus 1n of eta n, we see that we actually kind of begin at the puncture set n and get an auxiliary variable eta n. Then we go down the chain, come to n minus 1, which is here, connects to the second factor, and here we pick up another term of such an auxiliary variable. So this combination here is just the sum eta n minus 1 plus eta n. And as we go down the chain, at each time we come to the next factor, we actually include in this argument the corresponding auxiliary variable eta I. Now the actual string integrals are obtained if all of these Eisenstein-Kronecker series are expanded with respect to these auxiliary variables, and then the components we find are products of GKs, and that's exactly how these integrands look like here. So to be a bit more concrete, let me briefly show the 2 and 3 point examples. So in the 2 point case, you have a simple integral or set 2 from 0 to 1. The Cobeniusian factor is a simple exponential, and this chain here is just one factor of Eisenstein-Kronecker series. In the 3 point case, we have actually 2 permutations of 2 and 3. This class of integrals is given by, can be summarized in such a vector of length 2, where we have 2 iterated integrations, a 3 point Cobeniusian factor, and these 2 chains. Now they have both 2 factors, where we first begin at sigma of 3, pick up an eta of sigma 3, and then go to the next puncture sigma of 2, pick up the other auxiliary variable, and we end at 1. Now let me modify this class of integrals in order to finally then be able to apply the elliptic KZB associator actually. And we modify them as follows. So first of all, we introduce an additional puncture. So we introduce this puncture between the punctures set n and 1. So here we introduce, it's actually just like we introduce another external state to the system with associated momentum K0. And then the new class of integrals is called set 0 tau and looks as follows. So again, let me go through this step by step. And please just bear with me. There are just only a few minutes more technicalities, and then I will show you the properties actually of these integrals. But I wanted to give you a feeling of how they're constructed anyway, because I think it's actually quite a canonic construction. So what is done here is, so for the set tau integrals, we actually, they're actually defined on the torus, which has just one puncture, the puncture at set 1 equals 0. The new integrals here are defined on the torus with 2 punctures, so set 1 and set 0. And what we do is, first we take this sequence here and split it into 2 pieces. So, and where we split it, we just put a 0 into it. So that gives us actually this composition of this permutation, and we can put the 0 in between anywhere. It's also possible that the sigma 0 and 1 are the empty sets. That means you have n possibilities to put a 0 into this sequence sigma here. That means coming from these n-1 factorial integrals here, we get n factorial integrals. Then in the integration domain, we don't integrate over the full A cycle, but just up to the set 0 puncture. The Koppe-Nielsen factor is modified just by including the puncture 0. That means we have effectively an n+1 point Koppe-Nielsen factor. And now what happens to these chains? So we take this chain, and again, where we split the sequence sigma in half, we also split the chain in half. The one part is still connected and still ends at 1. That is what gives us this factor. And the other part now has actually a loose end. It doesn't end at the puncture which is not be integrated over. And that's where we attach it actually to this additional puncture here, the 0. This gives us this factor here. So again, to be a bit more concrete, let me show the 2- and 3-point example. So in the 2-point case, we have actually just one set tau integral that gives us 2 sets 0 tau integral, depending on whether we put the 0 after or before the 2. The first component of this vector is given by this integral. It's an integral up to set 0 with the 3-point Koppe-Nielsen factor and actually these 2 chains, but one is just a trivial. Or maybe I should have said that if one of these sequences sigma 0 or sigma 1 is empty, we just define this to be this actually trivial chain here. So a bit of more generic example is the 3-point case where we have 2 permutations of 2 and 3. That means we can put the 0 before, in the middle, or after these 2 entries. That gives us actually 6 integrals in the class of set 0 tau. The first component, for example, looks like this integral. It's an iterated integral up to set 0 with an effective 4-point Koppe-Nielsen factor. And again, this trivial chain. Non-trivial example is the third component. Here we actually really cut this sequence 2 and 3 in half and leave one part of this chain still attached to the 1 and then attach the other to the 0. So now I hope this weren't too many technicalities. Now let me just consider this full endpoint vector set 0 tau. In the endpoint case, what happens if we differentiate it with respect to this auxiliary insertion point set 0 is the following. We actually recover an elliptic KZB equation. And here in this equation now, as already announced, these xk's are n factorial times n factorial matrices. They are explicitly known, so we can give the exact linear combination we find here on this right-hand side. They're of degree 1 in, they're homogeneous of degree 1 in the Mandelstam variables. This means linear in alpha prime, and they are homogeneous of degree k-1 in the auxiliary variables. So now we have a solution of the elliptic KZB equation at hand and can therefore consider the 2 regularized boundary values I introduced before. And what we find is that these 2 boundary values include the n+2.3 level and the n.1 loop string integrals. In the first case, we take the limits at 0 going to 0, and in this case, we find that the first n-1 factorial components of the resulting vector indeed just contains a basis of the n+2.3 level set integrals. The other components are just related by BCJ relations to these first components. That means we can write this vector as an n factorial times n-1 factorial matrix times this vector here. A similar story holds if we take the limit set 0 going to 1. In this case, we find after a basis transformation to the eigenspace of x1, which corresponds to the eigenvalue value minus S01, we find also that in the first n-1 factorial components, we find the full basis of set tau integrals, the endpoint set tau integrals. maybe I should say actually here the effective one loop Mandelstam variable associated to the puncture Z1 is not just given by the S1j used in the definition of the Koba-Nielsen factor in the Z0 tau integrals, but it's actually the sum of the S1j plus S0j Mandelstam variables. That is actually what is going to give us this nice geometric interpretation, but I'm coming to that very soon. Again, here, all the other components are related to these first components by shuffle identities. That means we can project out the first components by a projection I call P, so that's an n-1 factorial times n factorial matrix, and get indeed just these tau, set tau integrals. So that means that we indeed recover these string integrals in the regularized limits Z0 and Z1, and hence we can apply the associator equation Z0 equals the elliptic KZB associator times Z1 equals the associator times Z0 to obtain an equation which relates these n-point Z tau integrals to the n+2 point Z integrals from tree level. And they're related by the elliptic KZB associator sandwiched in between this projection P and the EU matrix. Now, what is really nice about this equation is that it can be used to calculate the alpha prime expansion of the Z tau integrals to up to any order we wish from the expansion of the elliptic KZB associator and the tree level Z integrals. The expansion of the latter is known from the recursion from genus 0, which uses the Drinfeld associator, and the expansion of the KZB associator, including the P's and U's, actually is just given by can be obtained from these words, from these letters, which are explicitly known. And in particular, since they're linear in alpha prime and homogeneous in these auxiliary variables, if you want to calculate the alpha prime expansion up to a certain order and only consider a certain component as certain coefficients in the expansion of the auxiliary variables, we only have to include here a finite sum of terms. And one can exactly determine which words contribute, and that's exactly how one can calculate in the end the coefficients of these Z tau integrals, which are the real open string and genus 1 integrals. So now, actually, to finish soon, let me come back to this geometric interpretation. And in order to do so, let us consider the degeneration of the Riemann surfaces we obtain when taking these two limits as Z0 goes to 1 and 0. So first of all, we have this class of iterated integrals, the Z0 tau integrals, which satisfies an elliptic KZB equation with the matrices xk. And from these matrices, we can build the matrix P, U, and the elliptic KZB associator. So now what happens if Z0 is sent to 0? What happens is actually we obtain a degeneration of the Riemann surface. So, and in order to extract the corresponding information, we actually also have to regularize this process, and we can do this by rescaling the whole complex plane here, modulo the lattice, by 1 over Z0. If we do that, and let Z0 go to 0, we see that actually all the lattice points, except for the one at the origin, blow up to infinity. So that is what gives us the effective n+2 point insertion of the genus 0 string integral, while the x1 the insertion point which corresponds to the origin is still given by this contribution here from the Z1, and the effective n+1 insertion point on the genus 0 Riemann surface is given by this auxiliary puncture here we introduced at the beginning. And if you do exactly this rescaling and this limit on the level of the integrals, that's exactly how we obtain the n+2 point Z integrals. And in these integrals, indeed, we also see that the Mandelstam variable associated to the puncture n+1 are just given by the ones which are associated to our auxiliary variable set 0. If you do the same game in the limit set 0 goes to 1, so but this time without this rescaling, we actually just close the integration along the A cycle, and the two punctures set 0 and set 1 merge together. So what we expect is actually that the corresponding momenta also add up in this limit. And that's exactly what they do, and what gives us this kind of geometric interpretation of gluing mechanism. So what we find in this limit and the proper regularization with the x1 is that we obtain the set tau integrals, but where we expect to find the one loop Mandelstam variable S1j, we just find this sum S1j plus S0j. And just to complete the picture, with our recursion or with this associator equation, one can now connect these two vectors of string integrals according to this equation here. So to finish, let me show this picture for the 2-point example. In the 2-point case, we already saw how this 2-vector set 0 tau integrals looks like. It's just given by such a vector of two Eisenstein-Kronecker series. It satisfies an elliptic KZB equation with these matrices. I hope the lower boundary of the screen is not cut. I'm not sure how you can see it, but anyway, here this one is the S12 Mandelstam variable if you cannot read it exactly. And what you can see here is that these matrices are indeed linear in Sij and homogeneous of degree k-1 in the auxiliary variables eta2, which are these variables in the second argument of the Eisenstein-Kronecker series. Now if we let Z0 go to 0 and do this rescaling or the regularization, we just find the Veneziano amplitude with the Mandelstam variable S12 and S02. And again, we see that we have a 0 where we expect actually to find the momentum which corresponds to the puncture at 1. On the other hand, if we let Z0 go to 1, we close the integration along the A cycle and obtain this Z tau integral, which I already showed you before in this talk. And again, these two integrals can then be connected via this associator equation here. And now to finish, I would like to point out that here in the exponent of the Z tau integrals, we don't just find S12 as we did just in the for the original definition of this Z tau integral, but we actually find this whole sum, and that's exactly what I was referring to when I was talking about this summing up of momenta and this geometric interpretation. So it really seems like we interpolate between these two geometries, and as we then connect these two using the associator equation, it looks like as if we would glue these two parts together such that these two momenta combine. So the momentum which is associated to our auxiliary punctures at 0 and the momentum at Z1. So with this example, let me summarize. What we did is actually we have constructed a class of iterated integrals on the torus, which generalizes the Z tau integrals, so the generating series of open string integrals at genus 1, which interpolates between the tree level and this one loop string integrals, and which satisfies an elliptic KZB equation. That means that the corresponding associator equation can be used to relate these two string integrals, so the n+2.3 level and the n.1 loop string integrals together. This associator equation then gives us the possibility to calculate the alpha prime expansion of the one loop string integrals, and here now I really mean the components of the Z tau integrals by just a finite number of matrices, all of which are explicitly known. And geometrically, one can think of it as a gluing mechanism of worldsheets where two external states of the n+2 point genus 0 worldsheet are glued together to form an endpoint genus 1 worldsheet. But as I said, it's really in the sense I showed you before of this merging of the punctures and combining of momenta, and how this gluing mechanism can be viewed. Now a brief outlook. It would be nice to actually complete the picture. So I actually called it a recursion, but actually it's just first step in a recursion if it would exist. So it would be nice to be able to calculate the string integrals at any genus G and for any number of external states N, just using matrix multiplication and such associator mechanism. So here, this row here at the bottom is actually just a genus 0 recursion with the Drenfeld associator. And now we established the next step to the higher genus. It would be nice to go beyond this and generalize this to any genus. It would be nice to embed it into the mathematical literature that is known, which is related to this associator, especially from Enriquez and so on. It would be nice to rigorously formulate it in terms of twisted Theorem theory, as the genus 0 recursion can be done, as it can be done for the genus 0 recursion and so on. It would be nice to have potential applications of this mechanism, of this recursive mechanism to other theories, especially to compute field theory amplitudes and so on. I mean, there are many questions related to having such a kind of gluing mechanism or recursive mechanism to calculate these integrals which are part of amplitudes. So with this, I would like to thank you very much for your attention, and please feel free to ask me questions now, tomorrow in the discussion session, or just at any time via email or whatever. So thank you very much.
Thank you. So let's again take a couple of seconds to unmute ourselves. Thank you. Are there any questions for André? You can just raise your hand or also write them in the chat. So actually, I do have a question. Can you describe what the main challenge is to go to general genus to repeat this gluing procedure?
The main challenge is, first of all, we have to actually know how these string integrals look like. I think it has already been mentioned how they can may look like using this Arkelov geometry stuff. And then there's also the problem that in this case, actually, we don't just have one integration cycle we have to complete. So if we then complete this integral, so assuming we can actually define a class of integral which interpolates between these genus G and genus G minus 1 geometry or whatsoever, there are then more possibilities to actually do that. So it depends on which, where we actually cut this, the corresponding Riemann surfaces into the lower genus surfaces and so on. So I think there are indeed some systematic obstacles that are new for higher genus, but yes, that's.
Thank you. Are there further questions?
Hey, I have one question, sorry.
Yes?
Yeah, so have you tried to generalize this formula to just for the ambiguous string? In there, maybe this will some limitation because they also use such nodal Riemann sphere.
Yes, so I'm not exactly sure if I understood you correctly. You asked me if we have tried it for ambitwister strings.
Yes, well, yeah.
Actually, that's indeed one way in which we hope to get some field theory results with such a mechanism. But I think I can't say much more. Actually, yes, we tried, or we're trying at the moment.
Okay.
Exactly.
Yeah, thank you.
Further questions? Yes, Axel?
Hi, so I have a question related to your wishful thoughts. Can you actually reverse this logic? I mean, it sounded like you could possibly compute an endpoint amplitude at genus H by increasing the number of points and going down in the genus. Can you also go the other way? So you want to decrease the number of points and increase the genus, so related to partition functions on higher genus Riemann surfaces? So I'm asking about the inverse of the object that you called phi.
Yes, exactly. So that would be like just a cutting mechanism in this sense. I'm actually not sure how such a mechanism might be constructed, just related to our construction. But I guess in principle, we just had to reverse this associator equation, but I can't say just right now how this actually can be done or if this is a sensible thing. But I guess actually the inverse, at least for the Drinfeld associator, is well defined. So I think it should in principle be possible, but I'm not exactly sure how one can write down the inverse of, for example, this elliptic KZB associator. But I guess it should actually be possible. But it's really just a guess. I'm not exactly sure about this. I have to think about this.
Okay, thank you.
Are there further questions? Also, maybe now is a possibility to direct questions also at our first speaker, Piotr. Okay, I cannot see any further questions. So let us reconvene 4:15, so in 3/4 of an hour, and recall that one talk later we'll also have the conference picture, and that we'll have the conference dinner tonight. I'll leave the room here open, so please feel free to discuss or yeah, share your coffee pictures or chat. So, and yeah, also of course ask any further questions you still have. I'll get a coffee myself, so see you later.